Recording? Yes. The other day I was happy to find my students asking for sort of a lecture on quantum mechanics. These issues that I don't necessarily feel comfortable like saying that I'm an authority on, but I am quite interested in the topic. But mostly I have questions about it more than answers. This guy here is Heisenberg, and most familiarly known for his Heisenberg's uncertainty principle, which states namely that the uncertainty in the momentum times the uncertainty in the position of a particle is greater than h bar. You can see if I go out to code cogs and paste that into there, you can see that that does produce a relevant equation. Now, the most concrete description of the Heisenberg uncertainty principle that I think I have heard has to do with the one-slit interference, or what's called Fraunhofer diffraction, and you have a wavelength of light coming through the wave, and you can have an uncertainty in the y position right here. So this would be delta y, and then as the photons come out, you get a spread over here, and in general most of the photons that come out come in this region, and if you take that, you get a new delta y that is related to this spread in the momentum of the y direction, and there is a way to associate this uncertainty in the change in momentum with the uncertainty in the position of the particle. Okay, let's come back and discuss de Broglie waves for a second. Looks like I've got a couple of videos talking about Heisenberg's uncertainty principle. One called Fraunhofer diffraction Heisenberg Fourier Fresnel Huygens. Okay, so I just watched this video about Fraunhofer diffraction Heisenberg Fourier Fresnel Huygens, and anyway, I have a couple of mistakes in it, and I just want to go through a summary of what's in that video. One of the things, there's a couple of equations, one from our physics books that goes theta min equals 1.22 lambda over d, and there's another version of it in my astronomy book that says theta min equals 0.25 lambda over d. And the difference between these two is in this version, theta min is given in radians, lambda in meters, and diameter in meters. In this version, theta min is given in arc seconds, lambda is given in micrometers, and the diameter is given in meters. Now, how do you convert between these two equations was something that I have kind of learned since I made that first video there, or second one. If I want to convert an equation from one set of units to another, the best thing to do is get all of the variables on one side and all of the constants on the other. So it's theta min times d over lambda equals 0.25, and you want to express that constant in terms of the units that are used. So this is 0.25. Theta min is in arc seconds. Diameter is in meters over, and lambda is in micrometers. And what I want to do then is take that number and just convert it into the desired units. So 0.25 arc second meters per micrometer. I'm going to multiply that by how many arc seconds are in, say, a degree. 60 times 60 arc seconds are in a degree, and then how many how many degrees are in a radian. There are 180 degrees in pi radians. And then I'm going to multiply how many micrometers there are in a meter. There are 1 times 10 to the 6th micrometers in a meter. And when I multiply all of those things out, I end up with 1.212 radian meters per meter, which is pretty close to the 1.22 that we have. So we have theta min d over lambda equals 1.212 radian meters per meter. And you can put that back in its original form, so that it goes theta min equals 1.212 lambda over d, and that is the original form of the equation in the other units in the textbook, in our physics textbook. Let's see what else came up in that video. The momentum of light, energy and momentum of a photon. Energy is equal to hf, and the frequency times the wavelength is equal to the velocity, which is the speed of light. So I can replace f with E equals hc over lambda. Now, the momentum of the photon is sometimes referred to as hk, k being called the wave number, which is kind of like a spatial frequency. K is equal to 1 over lambda, so this is the momentum of the light is h over lambda, which also happens to be hf over c, if you wanted to do it that way, but we're going to use this form. And let's see, what else did I want to do? I wanted to use theta min equals 1.22 lambda over d, and then what I want to do is talk about the momentum. Let's see, this concept behind the momentum is I've got that photons coming in with momentum p, and they diverge this way and this way. I could say that this p sub y is going to be equal to, if this is theta min, let's say that's theta min, then this is going to be p sub y is going to be p sine, or maybe p tangent of theta min. Is it tangent? If this is p, well, or is this p? Well, one of those is p. Anyway, if the angle is small enough, it really hardly matters, because if the angle is small angle approximation says theta min equals tangent theta, as long as it's in radians, min equals sine theta min, and that's what I'm going to do, is just make this claim that p sub y is just equal to, or at least approximately equal to, just p theta, because that'll be assuming a small angle. So assuming a small angle. And when I plug that in to the equation up here, what will we have? Or can I plug that into the equation up there? Lambda will replace, let me see, I got this written on a piece of paper. I'm going to remodify this equation. P equals h over lambda, and so this will be my step 1. Replace lambda with h over p. Step 2, I'm going to replace this d. D is going to be called delta y. And finally, theta min 3 theta min is equal to p sub y over p. P sub y over p. And so I'm going to just take those three things and plug them into that equation there and see what happens. Theta min, I should copy all of that down and see what we've got here. Erase some of these extraneous details. Oh wait, here we go. Here's an eraser. That's not very big. There we go. Okay, and this is what we're going to stick in that equation. So what do we have? Theta min p sub y over p equals 1.22. Lambda is h over p, so I put an h over p there, and the diameter is delta y, and so as a matter of fact, let's just go ahead and call that delta p sub y too, because that's kind of the uncertainty in the momentum, because it spreads out over that region. Alright, now I'm going to take this delta y over here. Delta y, delta p sub y equals 1.22h. And this satisfies what's known as Heisenberg's uncertainty principle, which says that sigma x times sigma p is greater than or equal to h bar over 2. Here's h bar over 2 is actually h over 2 pi. So this, is it going to satisfy this? Maybe it's less. So as long as this delta x, delta p, as long as 1.22h is greater than or equal to h bar over 2, I'm going to put a question mark there, because if this is greater than h bar over 2, then we're satisfying Heisenberg's uncertainty principle here. So is 1.22h greater than or equal to h over 2 pi times 2? I would say yes, because this is 1.22h greater than or equal to h over 4 pi. 1 over 4 pi is considerably less than 1, so this is definitely greater than 1 over 4 pi h. But it's on the same order of magnitude anyway. So in this situation, at least, we're showing an uncertainty that is on the same order of Heisenberg's uncertainty principle. Now let me just mention a couple other things that I would like to get to maybe today or Thursday in class, talking about the Schrodinger equation. Basically, the Schrodinger equation is a statement of total energy equals kinetic energy plus potential energy. Now, kinetic energy is described in terms of p squared over 2m, and the p squared over 2m is basically 1/2 mv squared. That's the more familiar form. 1/2 mv squared is equal to 1/2, say, m squared v squared over m, which is equal to p squared over 2m. But anyway, this is the p squared over 2m for kinetic energy. And right now, I think the potential energy is just handled by some kind of function, but I forget exactly. Let's look at Schrodinger's equation to see what it exactly looks like on Wikipedia. Here's a nice wave function. Anyway, I h bar del t phi of rt equals negative h bar squared over 2m del squared phi of rt plus v of rt phi of rt. Now this nabla squared, that's called a nabla, has, or a del, usually called del, but the nabla is how you would enter it into, like if you are using latex or something. Anyway, that is called the divergence of the field, and it has to do with how, if I have a wave that's going like this, the divergence tells me how quickly it is coming down. If the potential field is going like that, it tells me how quickly the thing is going up or going down, and that is associated with the wavelength, and the wavelength P is associated with lambda over H, we're discussing, is associated with H over lambda, so that del squared pops out an H over lambda from the function. Now, a little bit of discussion is in order of like what kind of function phi of RT is. How could this represent the total energy, and this represent the potential? Well, obviously this V of RT in some way represents the potential energy. It's just basically that V should put you in mind of voltage or potential. But this total energy, and which is with respect to time, and the del squared, which is with respect to space. These things actually, when they operate on the wave function phi, they actually pop out energy terms and momentum terms. You can also see that p squared over 2m, actually each time you do the del function, it pops out a momentum term, and that 2m there is leaving that 2m on the bottom. But anyway, what kind of function is phi? Phi is equal to the wave function. Here's some examples of wave functions trapped in a one-dimensional energy well, I guess. But oops. And here are wave functions associated with the hydrogen atom. You can see like the S shells are circular. Here's the S shells. P shells. Well, I'm not exactly sure which ones are P shells, D shells, and F shells, but they're basically they're places in the hydrogen atom where things can kind of form. Anyway, let's see if we can find a particular expression of the wave function. Here it is. E to the negative IP x over h bar. This isn't exactly what I wanted. I wasn't but it's kind of close. The main thing is this e to the I px over h bar, and when you take the derivative of this thing, the partial derivative of it with respect to x, you end up popping out a momentum. So since I'm not quite able to find what I'm looking for on there, let's say the equation for this is something like e to the negative I kx minus omega t. Now if I take the derivative of phi with respect to x, say d phi dx, let's make that a partial derivative because I don't want to d phi dx, and divide that by phi. Then I'm going to get, I would just pop out the negative I k e to the negative I k x minus omega t. This is the fancy thing about taking derivatives of exponentials to the natural logarithm. All you got to do is pop that out, and you don't have to worry about anything else. And then if I divide that by the original function, e to the negative I k x times omega t, guess what I get? these cancel, and you get just negative ik. If I do that twice, I'll end up with negative ik squared, and still this will stay there and cancel out. If I do that and end up doing this division, negative 8, multiplying that by h bar squared over 2m, I end up with a total negative h bar squared over 2m. I end up with basically h bar k squared over 2m, which is the kinetic energy of the particle or photon. Similarly, if I take I bar del phi del t over phi, then I end up with a derivative. We'll pop out the omega, which would be I, like if I had I up there, it'd be I omega phi over phi, and we end up with that, and then I multiply that by I bar over I bar, and so that becomes h bar omega, and that gives us the total energy in the system, which has, for whatever reason, has more to do with the time domain than the frequency domain. Now there's a lot more to say about this, a lot more that I need to research about it, but this is some of the essentials. The other major aspect of quantum mechanics probably deals with Debroglie waves, the phase velocity and group velocities. One of these, I believe phase velocity is the omega divided by k, and the group velocity is t omega over dk. And you'll find with Debroglie waves, the group velocity are well studied in my, or kind of the k number is, remember, is equal to 1 over lambda, or 2 pi over lambda, I think. Kx equals 2 pi over lambda. I think 2 pi x over lambda. Yeah, I think that's right. Anyway, they have done a lot of measurements of interference with like electrons and stuff like that. So they've got a very good measurement of the wavelength of particles. But the description of the actual frequency they don't talk about very much. At least I've, and the one discussion I have a good example of, which is, I believe, in this Modern Physics Lecture 9, Phase and Group Velocity Dispersion. He does a calculation of group velocity in here, where he doesn't take into account the relativistic nature of the problem, and he does, when he figures out the phase frequency, he says that it's actually meaningless, or when he figures out I think the phase velocity, he says the phase velocity of a particle is meaningless, because he does the non-relativistic version. But the phase velocity, if you do a relativistic calculation of it, is kind of interesting. The phase velocity of a stationary particle is infinite, and the phase velocity of particles that are not what do you call it? Are not stationary, moving particles. The actual phase velocity actually kind of goes, if you have the particle going like this in space time, and this is the speed of light, then the phase velocity is kind of like kind of like this. The phase velocity and the group velocity are related by the term, by v. Let me see if I'll pause it for a second. Well, let me put it this way. In units where c is equal to 1, the phase velocity is equal to the reciprocal of the group velocity, if I've calculated right. This is kind of similar to the equation for a slope and its perpendicular slope. When you have two perpendicular lines, you get m perpendicular is equal to negative 1 over m. But for phase velocity and group velocity, you get this kind of 1 over, you get this reciprocal nature. And so you can see if the group velocity was 0, you would get v phase being 1 over 0, which is infinity. But I thought that was kind of a interesting thing that if you do this, if you plug in these numbers, the group velocity is what you would expect is the velocity of the particle. But this comes out to be 1 over velocity of the particle. With Debroglie waves, if you do it relativistically, might get around to showing that if I remember how to do it.